In this video, we'll continue our discussion of time-dependent electromagnetic perturbations by talking about stimulated and spontaneous emission. We'll start by reviewing absorption of electromagnetic radiation, then introduce stimulated emission, talk about incoherent perturbations and how they affect stimulated emission, and finally spontaneous emission. So if you recall, we had an example of an atom in the presence of an electromagnetic wave with a very long wavelength. Under those conditions, the electric field has no spatial dependence, so that its E0 is a constant value which has a time-dependent oscillation in a particular direction, in this case z. The perturbing Hamiltonian matrix element is equal to minus the polarization P times E sub 0 times cosine of omega t. And the polarization is just the charge times the matrix element psi b z psi a, where psi a is the lower energy state and psi b is the higher energy state. This leads to a transition probability from state psi a to psi b, which can be written as P sub A to B of t is equal to the polarization modulus squared, E sub 0 squared over h bar squared, sine squared of omega 0 minus omega t over 2, divided by omega 0 minus omega squared, where omega 0 is just the difference in energy between state B and state A divided by h bar. So this represents the probability of an atom absorbing electromagnetic radiation and rising from state A to a higher state B. So this is an absorption probability. What if the atom starts in the upper state, however? If it starts in the upper state, we can say that Cb, the coefficient of the upper state, at time equals 0 is equal to 1, and Ca at time equals 0 is equal to 0. And we can go through the same derivation that we ran through before for absorption, but now for the starting state being the higher energy state. Well, under these conditions where Cb of 0 at time 0 is equal to 1, the first order correction for Cb is nothing because it remains at 1. But Ca has a first order correction given by approximately minus I over h bar VAB, integral from 0 to t, cosine of omega t prime e to the minus I omega 0 t prime dt prime. If we expand the cosine of omega t prime and then combine the exponentials, we get minus I v sub ab over 2h bar, integral from 0 to t of the quantity e to the I minus omega sub 0 plus omega, all times t prime, plus e to the I minus omega 0 minus omega times t prime, all integrated over dt prime. So we have in green now note that we have minus omega 0, where before we had plus omega 0. Well, when we do those two integrals, we get minus VAB over 2h bar, and then the quantity e to the I minus omega 0 plus omega minus 1 over minus omega 0 plus omega, plus e to the I of quantity minus omega 0 minus omega, all times t minus 1, over minus omega 0 minus omega. And now, when omega is close to omega 0, this second term is very small, and this first term is large, so we can ignore the second term. And our final expression for Ca then is equal to VAB over 2h bar. And now we're going to factor out a omega 0 minus omega from the denominator. And from the numerator, we're going to take a e to the minus I omega 0 minus omega divided by 2. And that will be factored out. So we then have e to the minus I omega 0 minus omega t over 2 divided by omega 0 minus omega, all times the quantity, e to the minus I omega 0 minus omega t over 2 minus e to the I omega 0 minus omega t over 2. Since VAB, which is the matrix element in front here, is equal to VBA, which is the polarization times the electric field, E sub 0 magnitude, then the probability of transition from the upper state to the lower state in the presence of an oscillating electromagnetic field can be written as P sub B to A of T is equal to basically C squared, which gives us P squared, absolute value, E sub 0 squared, sine squared of omega 0 minus omega t over 2, divided by h bar squared times omega 0 minus omega squared. Now, as it turns out, this is a little bit surprising, and it's a purely quantum mechanical result. This is called stimulated emission. And this is the stimulated emission probability. And it turns out it's identical to the absorption probability that we calculated before. So if you look at these two expressions, they're exactly the same. So stimulated emission and absorption are two sides of the same coin. There's a perfect symmetry between the two. Now, if we look at all of this, we say the initial calculation we did represented absorption. So you start at a lower state, and you transition that state to an upper state with the input of a photon, or electromagnetic radiation, or a photon. The second was stimulated emission, which is a purely quantum phenomenon. That is, you start in the state, the upper state, E sub B, you send in photons, and you drop down to the lower state, emitting a second photon, an additional photon. Well, what about the process that we see all the time in nature, which we would call spontaneous emission? So if you have an atom in an excited state, it spontaneously will emit radiation and drop down to the lower state. We observe this all the time. This, however, would be E sub B dropping down to E sub A and emitting a photon. Well, theoretically, it can't happen because you need an oscillating perturbation, a sinusoidal perturbation, to stimulate either an absorption or an emission event. And a stationary state like E sub B or E sub A wouldn't decay. They don't change in time. But this theory is not complete. So if you add in quantum electrodynamics, you'll find that there are always radiation fields present, even in the ground state. And these spontaneous, radiation fields that are there will cause spontaneous stimulated emission. So far we've talked about sinusoidal perturbations. What if you have non-sinusoidal perturbations? That is, you have a broad range of energies. The sinusoidal perturbation has one energy or one wavelength. You have a broad range of energies and all polarization, so it's not always polarized in one direction. Well, we consider this start by considering this with the energy density of an electromagnetic wave, which we'll call U. And U is equal to epsilon 0 over 2 times the electric field squared, magnitude squared. So we know also the probability of an excited state doing stimulated emission under a monochromatic radiation perturbation, and that's P beta A, which we calculated before, and we have P beta A of T is equal to E sub 0 squared over H bar squared, polarization modulus squared, times the sine squared of omega 0 minus omega t over 2, divided by omega 0 minus omega squared. And we now can replace the E sub 0 with our expression for U, so we have 2U over epsilon naught h bar squared times the same quantities as before. Now, for polychromatic radiation, we can extend this by substituting for this energy density U and integrating over omega. So U can be replaced by an integral over d omega of the density of radiation as a function of omega. So rho of omega d omega. That means that my integral becomes this. My probability of transition from B to A as a function of time t is equal to 2 over epsilon naught h bar squared, polarization squared, integral from 0 to infinity, because we got to integrate all radiation wavelengths and frequencies, rho of omega sine squared times quantity sine squared of omega 0 minus omega t over 2 divided by omega 0 minus omega squared d omega. So basically we took the u and replaced it with rho of omega d omega and then integrate over all omega. Now, because the transition probability P of A to B or P of B to A is highly peaked about omega 0, that's this quantity here, is highly peaked about omega 0, we can simplify this integral by a substitution. The substitution is rho of omega becomes approximately rho of omega 0. And so we replace that in, we have rho of omega 0. But this means we can pull this out of the integral. If we now make a substitution that x is equal to omega 0 minus omega t over 2, so this becomes sine squared of x, and dx becomes minus t over 2 d omega, my integral becomes the following. P of b to a of t is equal to 2 over epsilon 0 h bar squared, the polarization squared, rho of omega 0, t squared over 4, times minus 2 over t. The t squared over 4 comes from the denominator here of omega 0 minus omega squared. Integral from omega 0 t over 2 to minus infinity of sine squared x over x squared dx. Well, this integral, then we can simplify by gathering all these terms and putting them together, and we get t over epsilon naught h bar squared, polarization squared times rho of omega 0. And now we've flipped the integration limits from minus infinity omega 0 to omega 0 t over 2. That got rid of the minus sign that we had here. And then we have an integral, the integral of sine squared x over x squared dx. This is now, we're going to make the assumption now that if time's long enough, then you're far out away from omega 0. And so we can replace this integral approximately with an integral from minus infinity to infinity, which makes the possibility of doing the integral much easier. So now we can say that P of B to A of t is equal to approximately t over epsilon naught h bar squared times the polarization squared times rho of omega 0, integral from minus infinity to infinity of sine squared x over x squared dx. And we know what that is. And when you do that integral, you get a final answer of pi over epsilon naught h bar squared, absolute value of the polarization squared, times rho of omega naught times t. So this integral basically boils down to pi. Now note that this probability no longer oscillates. It depends on the energy density of the radiation at omega 0, but it increases monotonically with time. All these other things are constants. So the Rabi flopping is gone, and the probability increases with time. We can now write a transition rate using this probability. The transition rate, which is the derivative of the probability basically, is just from B to A of t is equal to pi over epsilon naught h bar squared, absolute value of polarization squared, times the density at omega sub 0. And it's a constant because the probability rises with time, the rate must be constant. We also now need to average over all polarizations, because right up to now we've talked about a single polarization, but with incoherent radiation you have all polarizations. Well, in that case we can replace the absolute value of the polarization by the polarization vector dotted into an arbitrary unit vector n, and then take the absolute value. So P then, the vector, is now no longer just in one direction, z, but now it's an overlap integral of psi b r vector psi a. So it now becomes a vector itself times the charge q. So if we want to calculate p dot n hat average squared, then we can do an integral. We integrate over 1 over 4 pi times p squared cosine squared theta sine theta d theta d phi. And that's just integration over all possible angles. When we do that integral, we get that p squared over 2 times minus cosine cubed theta over 3 evaluated from 0 to pi. And when you do that all together, you get 1/3 times the absolute value of p, the polarization squared, is equal to the average polarization squared.